Welcome friends, Igor is here, and in this video we will learn how to compute an inverse of a non-singular matrix. First, we will discover a method for computing an inverse of a non-singular matrix, and then we will apply this method to compute this inverse. Let's get started. It's about time to define the notion of standard unit vectors. These are column vectors that have the following property. For the vector ej, the ith component is equal to 0 if I is not equal to j, and it is equal to 1 if I is equal to j. If you write out an explicit example of these vectors in one dimension, let's say dimension 4, then you should quickly recognize that these vectors are actually columns in the identity matrix. Now, let's just jump off the cliff and try to compute an inverse of this 5 by 5 matrix. An inverse of the matrix A, if it exists, let's say it's a matrix B, must satisfy two equalities. First of all, A times B must be the identity matrix, and B times A must be the identity matrix. Well, let's start by trying to find the matrix B that satisfies at least one of these equalities, namely the equality A times B is equal to the identity matrix. So the matrix A is given, and we are looking for the matrix B which satisfies this equation. We are going to represent matrix B by its columns, and we call the columns of the matrix B by B1, B2 up to B5. And we also represent the identity matrix by its columns, and we already know that the columns of the identity matrix are the standard unit vectors. To compute the matrix product of the matrix A with the matrix B, we recall the definition of this product. The columns of the product matrix are matrix vector products, where the matrix is the first matrix A, and the column vectors are the columns of the matrix B. Now we can view this last equality of two 5 by 5 matrices as equality of the columns. The first column of the matrix on the left-hand side is equal to the first column of the matrix on the right-hand side. The same is true for second, third, and all the way up to the fifth column. But these 5 vector equalities can be regarded as linear systems, where A is the coefficient matrix, the standard unit vectors are the vectors of constants, and the columns of the unknown matrix B are our vectors of unknowns. We need to find the 5 unknown columns of the matrix B, and therefore it means we have to solve all these 5 linear systems. But let's keep the following observation on the backs of our minds. All these 5 linear systems have the same coefficient matrix A. They differ only in the vectors of constants. But enough talk, let's get to the task of solving the linear systems. To solve the first linear system, we write its augmented matrix. This augmented matrix consists of the matrix A as the coefficient matrix and the standard unit vector E1 as a vector of constants. You apply the Gauss-Jordan elimination to find the reduced row echelon form of this matrix, and what is shown is the result of this reduction. Notice that from the reduced row echelon form you see that the linear system has a unique solution. Moreover, the solution vector of this linear system is actually the last column in the reduced matrix. This means the vector B1, which is the solution vector to this linear system, is given as the last column in the reduced matrix. Let's do this again for the second linear system. We again construct the augmented matrix, which consists of the same coefficient matrix A, but now the vector of constants is different. It is the second standard unit vector. We also apply the Gauss-Jordan elimination to this matrix, and we obtain the reduced row echelon form. From the reduced row echelon form, we see that this system also has a unique solution, and moreover, this solution is given by the last column of the reduced matrix. So the column vector B2 that we're looking for, which is the solution vector to this linear system, is equal to the last column of the reduced matrix. We do the same for the third system. We construct augmented matrix, we reduce the augmented matrix. We see that this system has a unique solution. This unique solution is given by the last column of the reduced matrix, and therefore the unknown vector B3 that we were looking for is equal to the last column of the reduced matrix. Now rinse and repeat. Linear system number 4, construct augmented matrix, reduce. Notice it has a unique solution, so this unique solution is given in the last column, and so this is the vector B4. Finally, the last fifth linear system, augmented matrix, reduce. Notice it has a unique solution. The unique solution is given in the last column of the augmented matrix, and therefore this is the vector B5 we're looking for. So we solved 5 linear systems in a row, and we computed all 5 columns of the matrix B. Now it remains to put all these columns together, and this is the matrix B we're looking for. Moreover, by our method of constructing the columns of this matrix, we are guaranteed that matrix A times matrix B is equal to the identity matrix. Does this mean that we have found an inverse for matrix A? Well, not quite yet, because what we found is a candidate for the inverse. At least the matrix B satisfies one of the two equations, namely A times B is equal to the identity matrix. But to be an inverse of A, the matrix B must also satisfy the other equation, namely B times A is equal to the identity matrix. But at least now you do have that matrix B in your hands, and you can check by direct computation whether the second equality B times A is equal to identity matrix is also satisfied. Now guys, don't tell anyone, but I'm gonna let you in a little secret. The second equation will automatically be satisfied. We'll prove it a little later. Now, I hope everyone is ready to complain about this approach, because this is not a super efficient method. We had to solve 5 linear systems to find one 5x5 matrix. That effectively means we had to perform the Gauss-Jordan elimination 5 times. But we can do better. Let's recall that all these 5 linear systems have the same coefficient matrix. Moreover, during those 5 reductions, you saw that this coefficient matrix A reduces to the identity matrix, which is a criterion for A to be non-singular. It means A is a non-singular matrix. And if you thought one step further, you would have realized that all these 5 reductions involved identical sequences of row operations. Because all the essential information, all the leading ones, all the pivot columns were already contained in the coefficient matrix A. So essentially, when you reduced the augmented matrix, you reduced the matrix A, and you simply had to keep track of what was happening to the last column, which corresponded to the vector of constants. This gives us the following genius idea. Why do we have to do the same reduction 5 times over? We can do the same thing in one single sweep. Because the reduction happens only on the level of the coefficient matrix A, and during this reduction all we have to do to the vector of constants is just to keep track of the changes to that vector as a result of reducing the coefficient matrix, then we might as well still reduce the coefficient matrix and at the same time simultaneously keep track of changes on all 5 column vectors that correspond to the vectors of constants. Here is what I mean by this. Let's construct one big matrix where the first 5 columns correspond to the matrix A. But then we also add all the possible vectors of constants from all the 5 linear systems. These vectors of constants are the standard unit vectors. And if you look at all these standard unit vectors as one whole, you will see that this is nothing but the identity matrix of size 5. So, As a shorthand, what we do is we write the matrix A, and then next to the matrix A, to the right of the matrix A, we write the identity matrix of the same size. Now, we perform Gauss-Jordan elimination on this one single big matrix. We know what's going to happen. The orange part, which corresponds to the matrix A, will reduce to the identity matrix. And then something will happen to the teal part, which starts as an identity matrix. But regardless of what this right teal part is, this matrix is in reduced row echelon form, because all the leading ones are part of the orange half. And this means now that you can read this desired matrix B as the right half of the reduced matrix. Keep in mind, this procedure works provided the matrix A is a non-singular matrix, so that we are guaranteed that the left half of the big matrix is going to reduce to the identity matrix. Now, let's summarize what we just discovered. Suppose we start with a non-singular matrix A of size n. Then we can construct a matrix of size n by 2n by placing the identity matrix as extra columns. We reduce this big matrix M to the reduced row echelon form, and then if we denote the right half of the reduced matrix by matrix B, then the matrix A multiplied by the matrix B is equal to the identity matrix. Now, let's be careful in using this theorem. Let's understand what it says and what it doesn't say. This result guarantees the following. If you have a non-singular matrix A, then you can always construct another matrix B so that A times B is equal to the identity matrix. However, this is only half of the requirement of an inverse of a matrix. For the matrix B to qualify as an inverse of a matrix A, you must also satisfy the equality B times A is equal to the identity matrix. And therefore, after you apply this procedure to compute the matrix B, once you have the matrix B, you can simply check by manual computation that the other equality B times A is equal to identity matrix is satisfied. Only then you can claim that B is an inverse of the matrix A. However, the title of the theorem suggests that this procedure does find an inverse of a non-singular matrix A. In fact, this title is not inaccurate. We will soon discover that the second equality, B times A is equal to the identity matrix, is automatically satisfied. So let's apply this method. In a previous video, I did a little bit of magic. I started with the matrix A, and then I pulled the rabbit out of a hat and I produced somehow a matrix B, which had a property that B times A were equal to the identity matrix. Of course, there was no magic trick on this. It was all based on solid math, and to figure out what this matrix B is, I simply applied the procedure we discovered in this lesson. I wish I were a kid again to believe in magic. If you found this video useful, and I hope you like magic tricks, then please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will discover many interesting properties of matrix inverses. I will see you later.